All right, last section, 8.4, polar form of complex numbers. So we're going to plot them and the absolute value, write complex and polar, convert between polar and rectangular, find products, find quotients, find powers and roots. All right, plotting complex numbers in a complex plane. All right, just like on a rectangular coordinate plane, you have an x and a y. On a complex plane, you have a real and an imaginary. So the real axis is horizontal. Your imaginary axis is vertical. So our real number represents the x coordinate of your point. So this is your A. Your imaginary is the y coordinate. So if I'm going to plot those, I'm going to go 2 to the right, and I'm going to go 3 down. 1, 2, 3. On B, there's my real 1. There's my imaginary 5. So right 1, up 5. All right, my real is missing from this one, so it's 0. My imaginary is negative 4i, which means I'm going to go straight down 4i. On D, we have the real, but not the imaginary. So we're going to go to the right, 5 units. Every number can be written as a complex. Okay, I can have, like my 5, can also be written as 5 plus 0i. I can make that look right. That's it. Every real number can be written as imaginary by adding a 0i to it. The absolute value, which is getting us into being able to change between complex and polar, or rectangular and polar, is finding the magnitude. Okay, the absolute value. All right, it measures the distance from the origin. All right, it's literally Pythagorean theorem. I have my real, imaginary, we use Pythagorean theorem. So find the absolute value here. We have the real, we have the imaginary, which is going to be a negative 1. So the absolute value of z, x squared plus y squared. If we just use the coefficient, that's going to be the square root of 7. Absolute value of z here. We have the real, we have the imaginary. And again, we just use the coefficient. Well, it's going to be 13. All right, here are the conversion methods for writing complex numbers in polar form and vice versa. X is radius, so that's magnitude. Cosine theta. Y is radius sine theta, where radius is the square root of x squared plus y squared. So we can get this angle. It's a reference angle. We get the angle. What am I trying to write here? I'm doing inverse tangent, absolute value, y over x. Reference angle. It all depends on where your complex number, what quadrant it is. All right, which we'll deal with. All right, so if we substitute those directly in, this is our rectangular form. X plus yi, a plus bi is what I call it. Then the a is our cosine. The b, our sine. Okay, you can factor out the r and say r cosine plus I sine. Sometimes we write it in this form, r cis theta, which literally means r cosine I sine, r cis theta. All right, expressed using polar coordinates. So first thing I want to do is find the magnitude. And I use 0 for x because the a is 0 here and the y for I. So it's going to give me a magnitude of 4. All right, I would say we're going to use inverse tangent here, but if we were to sketch this, for I, since it's imaginary, falls up here. It's quadrantal. So the angle is 90 degrees, or we can think pi over 2. Okay, so inverse tangent wouldn't work here. All right, so our complex number equals cosine 90 degrees plus I sine 90 degrees. I'm going to write it in the other form, but use pi over 2. So for this, pi over 2. I forgot this last one here. You could also write it just factored out. Okay, all of these are acceptable. Make sure you follow the directions, whether it wants degrees versus radians. This is -4 plus 4i, so that makes x -4 and y 4i, so that's going to put us in quadrant 2. Let's find the magnitude. So that is the square root of 32, which reduces to 4 root 2. Your reference angle, inverse tangent, opposite value, y over x. So this is the inverse tangent of 1, which is, again, we can use degrees, radians. I'm going to use radians here. It's pi over 4. Okay, but we're in quadrant 2. So theta is 3 pi over 4. Okay, so our complex number, radius cosine theta plus I sine theta. Okay, we can of course do that factored out. Oops, forgot the radius there. We can do it factored out. My gosh, I'm doing great with that I. So these two examples, we went from rectangular to polar, and now I'm going from polar back to rectangular. And so we want the x, which is radius cosine of your angle, and we want the y, which is radius sine angle. All right, so cosine pi over 6 is root 3 over 2. And then sine is 1/2. So then b equals 6 root 2 plus 6i. Okay, this one we have radius is 13, tangent theta is 5 over 12. So this is y over x, and we know from our formulas that x is our cosine and y is our sine, so we need cosine and sine here. I have the radius. Okay, so cosine would be 12 over 13. Sine would be 5 over 13. All right, so then x equals radius times cosine theta. Y equals radius sine theta. So our complex number is 12 plus 5i. Okay, so now we're going to be finding products of complex numbers that are already in polar form. The key is that they are already in polar form. So they're in the r cis theta form. So it's pretty straightforward formula. It looks awful, but it's not bad. But again, I'm giving you this formula. You multiply the two radius together, add the two angles together. That is it. So if I want the product of z1, z2, I'm going to multiply the two radius together. So that's 4 and 2. And I've got cosine. I'm going to add the two angles together. 80 plus 145. So 8 cosine, and for whatever reason I cannot think of what that is. $225. And that's honestly it as far as using this formula. It's not complicated. Multiply the radius, add the angles. The quotient rule is pretty similar. Again, the key is that they're already in polar form. They have to be. So r cis theta. Instead of multiplying the radius, you divide the radius. Instead of adding the angles, you subtract the angles. That's the difference. 1 divided by z2. Divide, quit moving, the radius. Subtract the angles. So 1/2. I'm just in the right frame of mind that I cannot do that in my head right now. 213 minus 33, 180. And that's it on that one. Okay, finding powers of complex numbers. So that's raising a complex number to a power. So a plus bi to some power n. All right? So z to the n says raise the modulus to that power, multiply the argument by the n. Okay, modulus is the word we're using for the radius. All right, so here's what it looks like. Oh my gosh. A complex number to a power. Put it in polar form first. Once it's in polar form, raise the radius to that power and multiply the angle by the power. So polar form first, radius to the power, multiply the angle by the power. So within this, we have powers of I that show up, and you did this in 1513, but let's review it. Anything to the 1 power is itself. Okay, but I need you to remember that that I is really the square root of -1. So if I'm doing I squared, that's really the square root of -1 times the square root of -1, which is -1. Okay, well, I cubed is an I squared times another I squared is -1. I to the 1 is itself. So this is -I. I to the 4th is an I squared times another I squared, because when you multiply it by the same base, you add the exponent, so it's I to the 4th. So this is -1 times -1, which is +1. And then the pattern repeats. So within this I to the 5th, I have 1 I to the 4th, and I have an extra I. Okay, so that's 1 times I, so I. And I to the 6th, I have 1 I to the 4th, but then I have a leftover I squared. So that's 1 times -1, which is -1. In I to the 7th, I have 1 I to the 4th and 3 leftover i's. So that's 1 times -I, because I got that over here. So that's -I. And then in I to the 8th, I have 2 I to the 4ths, because 4 plus 4 is 8. So it's 1 times 1, which is 1. So we figure out how many I to the 4ths we have in there, and then look at the leftovers. That's it. And the way we figure out how many I to the 4ths we have is divide the exponent by 4. All right, well, 9 goes into 4 twice. That means I have 2 I to the 4ths, but I have a remainder of 1. So I to the 1. Well, I to the 4th, 1, and I to the 1 is I. Okay, I to the 31. Now, I'm not going to write all the i's or the 4ths on this one. We're going to take 31 and divide it by 4. All right, well, that's 7. That means I have 7 I to the 4ths. I don't want to write it like that. It means I have 7 I to the 4ths. All right, well, I to the 4th is 1. So I'm multiplying 1 by itself 7 times. This is 1 to the 7th power. But I have a leftover. All right, there are 3 leftover. Well, I to the 7th is 1. Excuse me, 1 to the 7th is 1. And I to the 3rd is -I, so this is -I. So what you really want to do is you look at this remainder. That's all you need to worry about. If we look at the remainder and think, okay, that's what I have left, because I know I to the 4th is 1. I just have a bunch of those. And I to the I cubed is -I. Over here, we looked at the remainder. Okay, again, I to the 4th is 1, so I don't need to worry about that. So if we look at the remainder, I to the 1, I. Okay, evaluate the expression using de Moivre's theorem. Okay, so the first thing, polar form first. All right, so 1 plus I is really 1 I. So we're going to get the magnitude. We're going to get the angle, and 1 is in quadrant 1. So when I find my reference angle, it's my actual angle. Inverse tangent, absolute value y over x. So that's pi over 4. Okay, so v equals radius cosine pi over 4 plus I sine pi over 4. We get there first. All right, so I am taking this and I am raising it to the 5th power. By de Moivre's theorem, I'm going to take the radius and raise it to that 5th power. So radius to the n power is the square root of 2 raised to the 5th power. All right, so what I see in this is square root of 2 times itself 5 times. So square root of 2 times itself is 2. We have another one there. And then we have the leftover, so that is 4 root 2. And then we want to take our theta and multiply it by the n. So theta is pi over 4. We're going to multiply it by the n, which is 5. Okay, so we put this back. Z to the 5th in polar form is 4 root 2 cosine 5 pi over 4 plus I sine 5 pi over 4. But my original problem was in rectangular, so I need to take this and put it in rectangular form. So x equals radius cosine theta. Cosine 5 pi over 4 is negative root 2 over 2. So that is going to be negative 4 times 2 over 2, so it's negative 4. Y is 4 root 2 sine 5 pi over 4. Also negative root 2 over 2. So z to the 5th, put back in its rectangular form, is negative 4 minus 4i. All right, finding the nth root. So finding the nth root is kind of like the opposite of raising it to a power. It's still a power, but it's a cube root or fourth root or a square root or something like that. Finding the nth root. And it is a unfortunately psycho crazy formula. We just have to know what to do with this. All right. So we have this random k's thrown in there. We have n is the root. Okay, so there's n and these k's, these are new for us. The n is the root. All right, so cube root, the n would be 3. A fourth root, the n would be 4, and so on. The k is the number of times we're finding the periodic roots. So k actually starts with 0. And then we go until we get to the n, but minus 1. Okay, so I'll show you what that looks like here in a second. So we've got a problem here, and I try to break it up into pieces. So this is what we determine first. Then we plug in, figure out the k's, and then we work them out. All right, so we determine the n first. It says find the roots. So n is 3. Okay. We have radius and theta. So I'm going to plug them into this formula here first. So z to the 1/3 equals r radius to the 1/3 cosine theta is 2 pi over 3, and then we're taking that over 3, plus 2k pi over 3, plus I sine 2 pi over 3, plus, this is lovely, 2k pi over 3. And then we'll reduce. Cube root of 8 is 2. 2 pi over 3. I'm going to do it up here. 2 pi over 3 is the same as taking 2 pi over 3, multiplying it by 1/3. So this is 2 pi over 9. This doesn't simplify yet. Okay, the next thing we do is we figure out our k's. Okay. Now, the number of our k's start with 0, and then we go to n minus 1. Well, our n is 3. So we'll start with 0. Well, n minus 1, 3 minus 1 is 2. 2. Now we're going to plug stuff in. We're going to start when the k equals 0. Okay, so we're plugging in to this formula now. And I've got it all simplified. We just needed to know the k. So 2 cosine 2 pi over 9 plus 2 times 0 times pi over 3. All right, so our 2 2 times 0 times pi, that's going to be 0, so those are going to go. Same thing over here, 2 times 0 times pi over 3, that's going to go too. So simplified, our first root is 2 cosine 2 pi over 9 plus I sine 2 pi over 9. All right, when k equals 1. So same formula. Two times 1 times pi over 3 plus I sine 2 times 1 times pi over 3. So then what we need to do is we need to add, we're going to get two pi over 3 here for both of these. So I need to, don't bother me. Okay, so I need to add the 2 pi over 9 plus 2 pi over 3. So 2 pi over 9 plus 2 pi over 3. Common denominator is 9. So multiply by 1, multiply by 1. So that's 8 pi over 9. All right, our last one is when the k is 3. So same process. Two pi over 9. 2 times 2, because k is 2. All right, simplify. And then, of course, we need to physically add the 2 pi over 9 and the 4 pi over 3. Common denominator 9. So multiply by 1. To go 3 to 9 is multiply by 3. So that's 14 pi over 9. So, lovely little formula going on, but if you break it up into its pieces, and I literally mean follow this, determine your n. Plug your n, r, and theta in, and then simplify. Figure out your k's, and then individually plug in each k, and work it out that way. Okay, and that brings us to the ends of TCC Math 1613.